first two here, just got the last three.
Okay.
This is what I really struggle with, is the whole
Summing.
language, yeah.
Okay, so now you're into forces, and you remember when we were doing like vectors? You'd say, okay, we've got a vector like this, and then one like this, maybe one like this. That's not a very good marker. Now, find the net vector, like add these three up, so you have like A, B, and C, and you want to find A plus B plus C. What would you do to add those up?
Add the x and y coordinates together.
Yeah, so you take this component, this component, this component, and this component. You'd add this one to this one, and this one to this one, and then put them back together at the end. So forces do the same thing. That's actually why we did so much practice with that, is because it's the same thing when it comes to forces. You'll have a free body diagram. So that's the one that we're working with, right? You got,
Let's see, so,
okay, gravity. You got a pushing force.
kind of a downward angle.
And friction?
Yep.
What kind of?
Kinetic friction.
Kinetic friction, okay.
Then force of gravity and the normal force. We already got those.
Okay. And then you decided what coordinate system to use, right?
Yes.
You said, well, it's probably going to be moving in this direction, so let's make our coordinate system that way too. Okay? And does it tell you what angle he's pushing the chair at?
I don't think it gives you a specific angle, it just shows you
Oh, okay.
that it's kind of downward.
So we'll just call it theta then. Okay?
Okay.
And it says, what's the first question you're looking for?
Use the component form of Newton's second law to write an expression for the x component of the net force.
Okay.
And
So this thing, you'll see all the time.
it's the sum of?
Yep. So sum of the forces in x. So which forces are in the x direction?
Let's see, the force of his push and the kinetic friction.
Okay. So with the force of the push, is it positive or negative?
I don't know, positive?
Yeah, because it's pointing this way on our coordinate system.
Okay.
So we determined this would be x and this would be y.
Mhm.
Usually you just write x or y at the positive end of each axis. Is it the total force of the push though?
Mm-mm.
So what would you do to the force of the push to get it just in x?
This, oh, I know this one. It's the theta times the cosine of, or the sine, no, cosine of,
So you actually do the force of the push times the cosine of theta.
okay.
Yeah. So yeah, exactly. You just want to break this down into its x component and its y component.
Okay, so force times cosine of theta.
Mm-hmm.
Okay.
Then the force of friction will be a negative, because it's pointing that way, right?
Okay.
So that would be your net force in x. So this is what they're looking for.
Okay.
And then you'll do the same thing in y. What would that be equal to?
Okay, so let's see. Be the force of the push times the sine of theta minus kinetic friction.
Oh, you want to do it in y though. So any force that's in y.
Oh, so 0. Isn't it?
No, so you got the normal forces in y. So that's anything that's going along the y axis. Right, so up and down. So you've got a normal force right here.
Okay.
You've got a force of gravity.
Oh, okay. That was throwing me off because they cancel each other, but we got the downward
Right,
push
right.
to consider.
So you want you wanna write these out, even though, cause you've also got this, force of the push times the sine of theta, you're right about that. That all equals mass times acceleration, which in this case will be 0.
Okay.
So actually, it turns out that these two don't cancel each other just by themselves, because you got a force of the push in there too. So even if they cancel each other out, you want to add up everything,
Okay.
because otherwise you'll miss something.
Was that the second one? It was.
Yeah, so those are your first two.
Okay, so, let's see, it's already got, so, I don't even know how to enter these in.
So the other one lets you do subscripts.
Okay.
So you do a capital F, and then you click that button. And you do P, and you get out of your subscript. Oh shoot, you highlighted it.
Dang it. Of course. Okay, so. Cosine, and then the theta symbol. Minus. You do a lowercase f?
No, I do it according to their,
Okay.
so their FK is capital, yeah.
Okay.
It won't take points off if you put the wrong case, but it will say it's incorrect and make you do it again.
Oh, okay. Okay.
It'll just tell you if variables are case sensitive.
So, force, the normal force. Minus force of gravity. Minus force of the push. Times sine of theta. Oops, I screwed it up. What did I do? Do I put equal 0?
Wait, what is it asking? Oh, variables are case sensitive, so no points deducted. So your normal force is N and G are capitals. Those are the only things.
Oh,
See what I was saying about that? Like, it'll just tell you it's not right, but it's probably just because you put the wrong case, so we didn't take any points off for you.
and p is lowercase?
Yeah.
I see.
Yep. There we go.
Okay. What is the magnitude of the acceleration of the chair? What is the magnitude of the normal force acting on the chair? Okay, so find magnitude, would we just add up the x and y coordinates?
So magnitude of the acceleration, realistically speaking, which direction is the chair going to accelerate?
To the right.
Yeah, only in X, right?
Mm-hmm.
You're not going to have it, it's not going to start floating, like floating up as this guy's pushing it. It's not going to dig down into the floor.
Right.
So you know that your acceleration will only be in this direction. You can say Fp cosine of theta minus Fk equals mass of the chair times acceleration.
Okay.
So then how do you solve for acceleration?
I
You just want to take this and divide it. So you do over the mass of the chair.
Okay.
So this would be your acceleration.
So walk me through the equation again, how we got that?
So you know that your force equals mass times acceleration,
Right.
but your force is usually a combination of a couple of different forces, so we'll call it our net force.
Oh, I see. I get it. So that's just, okay, yeah, because in my head I was thinking, well, it's just the x value minus the friction. So-
Right, so this this x value minus the friction will give you the force in x, but force and acceleration aren't the same, they're just related by ma. So if you have the force in x, it's really quick to find the acceleration in x, you just have to divide by the mass.
I see.
So, I mean, and you just kind of remind yourself of that by saying, well, if this thing weighs 2 pounds, it's going to accelerate a heck of a lot faster than if it weighs 200 pounds.
Right.
So, okay?
Okay, so, let's see here. So F, come on. P times the cosine. Sine of theta minus kinetic friction. Wish there was a faster way to enter these. And it's, was it uppercase K or lowercase? Looks like lowercase.
It's the lowercase, yeah.
And how do I just do divided by?
Oh, shoot. Yeah, you actually have to put the divided by symbol in first.
Oh, if I put this in brackets and then will it accept it like this if I do?
No, I don't think so.
No.
Try it. Now hit your divide button up there. There's actually a divide button that they have.
In this one?
Yeah, see A over B, just that fraction button.
Oh, right here, right.
Yeah, see it makes you type them in above and below.
Okay.
But anyway, we're almost out of time, so real quick. We said that our acceleration in y would be 0. So we can find the normal force. Oh, well, what am I doing here? So we know the acceleration y is 0, so that makes this side of the equation 0. So we can take these two and move them to the other side. We can say our normal force is going to be equal to Fg plus force of the push times the sine of theta.